In this lesson, we're going to be using all of the skills that we've learned about graphs of a function to come up with an accurate sketch of a function. So we'll be using the first and second derivatives test to look at increasing, decreasing, relative extrema, and concavity, limits at infinity, and also some review skills from Algebra 2 such as x and y intercepts to piece all of this information together, not only to describe what a function looks like, but to help us and aid to graph without the use of technology. So just as a quick recap, these will be the particular graph features that we're interested in today. We'll be looking for the x and y intercepts, the domain of the function, where the vertical asymptotes are located, the relative extrema and critical numbers, the intervals of increasing and decreasing, possible inflection points and inflection points, intervals of concavity, and end behavior. So let's just get going right away and do an example. So we'll be looking at this rational function f of x is equal to 2 times quantity x squared minus 9 divided by x squared minus 4. So we can start by filling in some of this pretty quickly. I'll try to take care of some of the maybe non-calculus items first. So if we want to go ahead and check out like what the y-intercept would be, you can go ahead at the y-intercept x is equal to 0. So if I go ahead and plug in 0 for x, I end up with negative 18 over negative 4, which reduces to 9/2. So we can go ahead and fill that one in. So my y-intercept is going to be 0, 9/2. Okay, the x-intercept for a graph is where the function is equal to 0, where it has a y value of 0. For a rational function, that's going to be where the numerator is equal to 0. For us, that's going to be at plus or minus 3. So my x-intercepts are going to be at 3, 0, and negative 3, 0. For a rational function, vertical asymptotes are where the denominator is equal to 0. So I take the denominator x squared minus 4 and set that equal to 0. So I get plus or minus 2. Alright, so the equations of my two vertical asymptotes will be at negative 2 and x equals positive 2. Alright, let's see what else is on the list. Domain we could fill in next. This function would be continuous everywhere except at the vertical asymptotes. So the domain is from negative infinity to negative 2, from negative 2 to 2, and from 2 to infinity. And then another quick piece of information that we can talk about is the end behavior horizontal asymptote. So remember that's why we learned how to do limits at infinity. So if I take the limit as x approaches positive infinity of 2x squared minus 9 over x squared minus 4, the power in the top and the bottom is the same, so the limit's going to be the ratio of the leading coefficients, so that's just going to be 2. Okay, so we can fill that in there. So the limit as x approaches infinity of f of x is going to be positive 2 for both ends. And that also means that I have a horizontal asymptote at y equals 2. So next what we have left is our first and second derivative work. Since that's going to end up taking up a little bit of space, I'm just going to continue on to the next page. So I'm going to want to start with my first derivative test work, finding where the derivative's positive, negative, and 0, so I can come up with the intervals of increasing and decreasing and go from there. Alright, so for derivative purposes, I'm going to say that the top is 2x squared minus 18. So when I go ahead and I take the first derivative, I have the bottom times the derivative of the top, which is 4x, minus the top times the derivative of the bottom, which is 2x, all over the bottom squared. We want to know where that's equal to 0 and undefined. we'll want to simplify that. One of the reasons we want to simplify this, besides that it makes the equation easier to solve, is we're going to be taking the second derivative, so we do want the simplest version of this function possible. So 4x squared minus 16x minus 4x squared plus 36x all over x squared minus 4 quantity squared. Alright, so it looks like these cancel. And I'm left with 20x on top and x squared minus 4 in the bottom. I'm going to keep the denominator in factored form because it'll be easier to solve. So we want to know where this is equal to 0 or undefined. Whoop. So the function's equal to 0 where the numerator equals 0. So I get one of my critical numbers to be at 0. Where this is undefined would be where the denominator is equal to 0. And that's going to be at plus or minus 2. So again, those vertical asymptotes come up again as critical numbers. So that was one of the things on my list. So my critical numbers are x equals 0 and plus or minus 2. So as soon as I'm done with that work, I want to go ahead and label that. Alright, so then I need to get my intervals of increasing and decreasing, so I'm going to run a first derivative test and do some test values here. Alright, so if I go ahead and I plug in some test values, I end up getting my first derivative number line to be, when I plug in something less than negative 2, I get negative, negative, positive, positive. So at 0, I'm taking a look at that. I see a sign change, so from decreasing to increasing on f, so I'm going to say that there is a relative min at x equals 0. There's neither a min or a max since there wasn't a sign change here at negative 2 or 2. I had asked for my intervals of increasing and decreasing, so this function's increasing from 0 to 2 and from 2 to infinity. And this function is decreasing from negative infinity to negative 2 and from negative 2 to 0. Alright, so then the next thing we need to do is describe the intervals of concavity and find any possible inflection points and inflection points. So let's go ahead and take the second derivative. The most simplified version of the first derivative being right there. Alright, let's use the most simplified version of our first derivative to come up with our second derivative work. So this f double prime of x is going to be the bottom times the derivative of the top, which is just 20, minus the top times the derivative of the bottom, so I bring down the power of 2, x squared minus 4 to the 1 power times the derivative of the inside, which is 2x, all over the denominator squared. So we'll want to clean this up so that we can solve. I do notice here, however, that I have a factor of x squared minus 4 in each part, so it probably would be fastest to go ahead and factor that out. I also have a factor of 20 in each of these, so I could take that out as well. So that's going to leave me with x squared minus 4 left because I had 2 of them here. And then I'm left with an x and then a 2 and another 2x, so minus 4x squared. Alright, so we clean that up just a little bit here. Can maybe bring that 20 out front. All right, so then we want to know when we're checking for pips where this is equal to 0 or undefined. So we start by looking at where this is equal to 0. So we take the numerator and set that equal to 0. Since this is already partially factored, I can see that solutions that I'm going to get are going to be plus or minus 2. And then this quadratic here is not going to yield any real solutions. Okay, so far I have pips there. If I set the denominator equal to 0, I end up just getting plus or minus 2 as well. So my possible inflection points, or my pips, are at plus or minus 2. So now I need to do some check some concavity work here. So I go ahead and I run a second derivative test. So now if I plug some test values in to the second derivative, like if I were to plug in -3, what I would end up getting is a negative second derivative. If I were to plug in 0, I'd get a positive second derivative, and if I were to plug in something like 3, I'd get a negative second derivative. Alright, so that would mean that this graph is concave down on the interval -infinity to -2 and from 2 to infinity. This graph is concave up between -2 and 2. And before we jump the gun and label -2 and 2 as inflection points, because there is a change in concavity there, remember that an inflection point implies that it's an actual point on the function. -2 and 2 are vertical asymptotes for this function, which means that those are two values that aren't in the domain of the function. So this actually has no inflection points. So just something to make note of even though there is a change in concavity, make sure that the values that you're looking at are actually points on the function. So let's try to use all of this information to come up with a sketch of the graph, because we actually know quite a bit of information. So we have vertical asymptotes at plus or minus 2, so we can sketch that in. We know that there is a horizontal asymptote at y equals 2. We knew that the x-intercepts were at plus or minus 3. The y-intercept was at 9/2, I believe, so that's 4.5, so 2, 3, 4, 5. All right, so back from some of our work up here, we know that the function's increasing from 0 to 2. Oh, pardon me, we want to start to go from right to left, or when we're writing this, so it's decreasing from -infinity to -2. From -infinity to -2, it's concave down. So decreasing and concave down. Similarly, the function's decreasing from -2 to 0, but then increasing from 0 to 2 because we had said that there was a relative min at 0. We also know that the function's concave up, so then we know what that branch will be doing. Similarly, I know the function's increasing from 2 to infinity, but concave down. So all of this information can give us a very clear picture of what this function will look like. So this example that we just completed was a rational function that had some messier algebra work, but not all of them will necessarily be that time consuming. If you found that you followed this process pretty clearly, since we didn't introduce any new skills, you're welcome to stop now. Our next example will be analyzing a more basic polynomial function where the derivatives aren't nearly as time intensive. Okay, so let's go ahead and look at the quartic. F of x equals x to the 4th minus 12x cubed plus 48x squared minus 64x. So let's try to get down some of those intercepts again like we did in the last example. So if I plug in 0 for x, I end up just getting 0. So my y-intercept is going to be 0, 0. If I go ahead and set this equal to 0, that would tell me what my x-intercepts will be. We can do a little bit of work to clean this up. We can factor an x out of everything. And then the rest of this here is not necessarily factorable with traditional methods. So if you end up plugging this into your calculator and solving, you end up getting x to equal 0 and x to equal 4. So that would make my intercepts at 0 and 4. Alright, so then vertical asymptotes, since this function does not have a denominator, there's no place where the denominator can equal 0, so there are no vertical asymptotes, which shouldn't really surprise us for a typical polynomial. In terms of horizontal asymptotes and end behavior, let's go ahead and do the infinite limit. If we're looking at the infinite limit, we don't have a denominator here. So if we were to insert infinity here for everything, I'd end up with infinity to the 4th minus 12 times infinity cubed plus 48 infinity squared minus 64 times infinity. Well, overall, that's just going to be a net value of positive infinity. If we were to plug in negative infinity, when we do negative infinity to the 4th power, that causes it to be a positive infinity as well. So since neither of those limits are approaching infinity, there are no horizontal asymptotes. And so our end behavior would just be what's listed up there. Alright, so in terms of domain, there isn't anything that I can't plug into this. I can plug it in negative numbers, positive numbers, and 0, so the domain is all real numbers. So let's go ahead and do our intervals of increasing and decreasing in our first derivative test work on the next page. So I go ahead and I take the first derivative. So 4x cubed minus 36x squared plus 96x minus 64. I want to go ahead and set that equal to 0. If we go ahead and use technology to come up and help us with the zeros on that one, we end up getting 1 and 4. So let's go ahead and get organized with our first derivative test. So if I plug some test values in to my first derivative, so if I were to plug something in like 0, I end up getting negative 64. If I end up plugging in something between 1 and 4 like 3, I end up getting like a positive 8, and if I plug in something like 5, I end up getting positive 16. So in terms of, so these would be my critical numbers. So if I'm trying to find out where there are extrema, I have a decreasing and then increasing, so there's going to be a relative min at x equals 1. There's not a max here at 4. The function is decreasing from negative infinity to 1 and increasing on the interval 1 to 4 and from 4 to infinity. Alright, so if we want to go ahead and get working on our second derivative work here, so I end up having 12x squared minus 72x plus 96. Alright, so we can go ahead and do some factoring to solve this quadratic. So if we take a 12 out of everything, I end up with x squared minus 6x plus 8 is equal to 0. And then this ends up factoring to x minus 4, x minus 2. So x is equal to 4 and 2, so those are my pips, so those are my possible inflection points. So go ahead and run a second derivative test. Alright, so if I go ahead and check this out, if I plug in something less than 2, I end up getting positive. If I plug in something between 2 and 3, I end up getting negative. If I plug in something larger than 4, I end up getting positive. So in terms of the function, that means f is concave up on the interval negative infinity to 2 and from 4 to infinity. Concave down between 2 and 4. And since there's a change of inflection at 2 and 4, there are actual inflection points at x equals 2 and 4. Okay, so let's use this information to help us sketch the graph. Okay, so we had said that the y-intercept was at 0. We had said that there was another x, there was an x-intercept then at 4. We had said that there's a relative minimum at 1. Since we don't have quite the same features as we had in the last example, we might want the y-coordinate for the original function when x is 1 so we can plot that accurately. It ends up to be, if we plug 1 into the original function, we get a y value of negative 27, which is pretty large negative number, so we'll just kind of rough sketch and put that down there. The end behavior had been positive infinity for this. And then the function was decreasing from negative infinity to 1 and supposed to be concave up. And then the function is increasing after that and then increasing some more. You can see that that matches up with that information that we had right there. Alright, so as you noticed, we just applied the skills that we had learned earlier in the unit to come up with some basic graph features like intercepts, but then also to give the intervals of increasing and decreasing, relative extrema, intervals of concavity, and inflection points to help us get an accurate sketch of the graph without perhaps using the graphing features of a graphing calculator.